Afternoon session. Our first presenter for the afternoon will be Stephen Hoover. He will present on Pystan, Bayesian interface for fun and profit.
All right. Hello, everybody. My name is Stephen Hoover. I'm a lead data scientist at Civis Analytics. Today, I will be talking about Bayesian Inference. I will tell you about the Pystan package. And hopefully, by the end of this session, you will have some idea how to fit a multi-level model in your own home, in your spare time. Fun is guaranteed. Profit is up to you, but I'll show you how to do it. So, what am I talking about when I'm talking about Bayesian inference? The really simple thing is counting. You're trying to figure out how many different ways something can happen. And the more ways something can happen, the more likely it is. The world is a certain way. We don't know what the world is like. We're trying to learn what the world is like. That's what we're trying to get at in machine learning. And in Bayesian inference, we're talking about randomness. We're talking about probabilities. It's all representing the state of our knowledge. And there are tools that will help you codify your knowledge and what that means for the parameters of your model. In particular, you have Bayes' rule. Bayes' rule is pretty simple. You have going in, you have your data, you have your prior knowledge, and coming out, you have the state of the world, your posterior probability. Taking a slightly closer look at this, in the center part of Bayes' rule, you have this p probability of y given theta and x. Here, y is your outcome. This is what you've measured about the world, your target, your outcome variable. The x is your features. That's what you know about the examples going in. And theta represents the parameters of your model. Now, parameters is whatever it is in your model that's tunable, but using linear regression as the basic example, the parameters are your coefficients. You're multiplying a vector of coefficients by your vector of features, and you get y. And what you're trying to do in inference is figure out what are those coefficients. What is the probability of theta given what you know about the world, the y and the x. But note that you're also putting in the probability of y given theta and x, which is your model. What do you know about how things happen? And some prior knowledge about the world. Whenever you're fitting models, this is in there somehow implicitly, but here we're going to be writing it down a little more explicitly. How do we do this? Probabilistic programming languages are a way of working with probabilities. The difference between a probabilistic programming language and something like Python is that in a probabilistic programming language, random variables are objects that you write down and use. In Python, you have your functions, you have your classes, you have floats and integers, but in probabilistic programming, you also have a variable with a normal distribution, a variable that's drawn from a Bernoulli distribution. There's a lot of examples of probabilistic programming languages. If you're doing this in Python or from Python, then I think the two primary examples are PyMC3 and Stan, or the Python interface to Stan is Pystan. Why would you be interested in taking this modeling approach versus fitting your model with something in scikit-learn, for example? I think there's a lot of reasons why you might be interested in using something like Stan. The really cool thing, in my opinion, about working this way is that you're writing down the data generation process. You're writing down what you know about where your data came from, and that is your model. And the software is going to solve for the parameters in that model. Also really important is that you get the uncertainty out. If you fit your linear regression in scikit-learn, sure, you get the best fit values of the coefficients. But if you fit a model in Pystan, then you'll get not just the best fit values, but you'll also get a distribution. This is telling you, given what you know about the world, what could possibly those values be, not just what's the most likely thing. You have a lot more flexibility in specifying your model. You can write down a wide variety of different combinations of probability distributions, codify whatever it is that you know about the problem. And of course, you can make use of your domain knowledge. There's two ways that this comes in. One is through the model itself. And whenever you're training a model, trying to learn about the world with machine learning, you're always implicitly codifying something about the problem with your model. For example, if you're using a convolutional neural network to classify photographs, the very fact that you have a convolutional network, you are claiming that there are different patches of your input, and that each patch that's nearby each other is similar to each other patch. Maybe you're not thinking about that when you're using the tool, but that's implicitly in there. And the second way, of course, is if you know something about the distribution of your parameters going in, then you can also codify that when you're using probabilistic programming languages. For example, if you're trying to find the height of a person, given some other information, you know that human beings are not 10 feet tall, usually. You know that human beings are not 1 centimeter tall. And so you can codify that knowledge. You can, for example, say that humans are probably between 1 and 3 meters tall. There's some distribution there. Stan in particular. Stan is an imperative probabilistic programming language. Imperative, as contrast with functional or object-oriented. Imperative is like C. It just means that you're executing statements one after the other. You're telling it to do things. Stan itself is a domain-specific language. When you write models in Stan, you write it with the Stan language. This has pluses and minuses. Minus, you aren't writing in Python, so there's this extra new thing that you need to learn. There's not a whole lot, though. I'll show you that in a few minutes. Plus, it's interoperable. Stan has interfaces in many different languages. R and Python, I think, are the two big ones. R and Python cover a lot of a huge portion of the data science community, so it lets you share models easily between different practitioners. Also, a really great thing about Stan is that it's completely open source. It's developed on GitHub. You can go to GitHub and see the current master version of their project, see the issues that they're working on, contribute to Stan. I'm not going to teach you about Monte Carlos or MCMCs, but just to give you a really brief look at what exactly Stan is doing when you tell it to optimize your models. The core of Stan is a Markov chain Monte Carlo algorithm. It's using Bayes' rule, which I showed you, to find the full posterior probability distribution of all of your parameters. And a Monte Carlo algorithm is using random draws from a probability distribution to do an integral, to integrate something. But often it's not really easy to draw random independent samples from an arbitrary probability distribution. But even if you can't do that, sometimes what you can do is use correlated random draws. And by correlated, I mean step from place to place. And on the bottom here, this is a crude cartoon of what's going on in a Markov chain Monte Carlo. You start in some random location. Here it's on the upper right. And you evaluate how likely is it, given what I know about the world, that these set of parameters are the correct set of parameters. And then from there, you step to another point. You ask how likely is this point. You step, 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 step. And you have rules for how you can step, how you transition. And eventually, you get to the core of the probability distribution. And you're stepping from place to place around it. At the end of the whole process, you throw away the first little portion of your steps, and you plot out all the rest of the steps. And you spend more time where there's more probability. You spend less time where there's less probability. More about Stan. There's many different algorithms for doing Markov chain Monte Carlos. Stan uses what's called a Hamiltonian Monte Carlo. It's actually doing Hamiltonian dynamics from physics. It's treating the probability distribution as a potential energy distribution. And it's pretending that you have some momentum vector going through there to take the steps. As part of this, they're doing auto-differentiation. They actually have a really good auto-differentiation algorithm because they need to find the gradients at each point in the probability space in order to figure out which direction they should be stepping. They're compiling your code to C, which means that it runs pretty fast. There's a lot of language features around having different probability distributions, features for improved numerical stability with common statistical operations. And as I mentioned, multi-language interoperability. At Civis, we have people who work in R and we have people who work in Python. And we can, when we use Stan to share models, it's really easy to communicate between people who work best in R and people who work best in Python. And of course, there's domain specialists, people who know a whole lot about statistics, and Markov chain Monte Carlos who are actively working on developing the project, which is a big plus for me. Okay, now I will switch to an IPython notebook and show you what this actually looks like. This will be up on GitHub at some point after this talk. All right, I will start again with logistic regression, and the session this morning was great because we also looked at logistic regression then, and if I were, sorry, linear regression. I will change that before I put it up on GitHub. Linear regression. If I were actually solving a linear regression, I would probably not be using Stan, but it's a good place to start. What you're looking at with linear regression, y equals beta times x plus epsilon, and we saw the y and the beta times x this morning. Epsilon is actually pretty important. That was implicitly in the equations before, but not shown. If you had y equals beta times x, then your data is a straight line. Great, you fit perfectly. Epsilon represents the extra unexplained variance in your model, the stuff that isn't captured by that linear relationship. And when you're fitting with ordinary least squares, when you're trying to minimize this, you're implicitly assuming that this is normally distributed, which is usually a pretty good approximation. This is what a Stan model actually looks like. It's set out in several different blocks. First, you have your data block, and this shows you all of the things that you're putting in. These are parameters that you're going to be passing in from Python. You have transformed data, which I'm not using in this model, but if you want to perform some calculations on the data, do some transformation, then you can do it here. It runs once in compiled C. Parameters, you're always going to have a parameters block, and this is the thing that you're estimating. The parameters for linear regression are your coefficients. And you'll notice that I'm also including epsilon, this extra uncertainty. So the model is going to also estimate how much variance there is around this linear relationship. Transformed parameters, like the transformed data, you can perform some transformation on the parameters if you want to model with them in a different form. This runs every step of your algorithm. The model, this is where you write down the model. And this thing here, y tilde normal features times beta epsilon, that's writing down the linear regression. It's saying that y is normally distributed with a mean described by whatever your feature vector is times your parameter vector, beta, and there's some scatter around there. Now, what Stan is actually doing when you tell it this is syntactic sugar for this increment log probability statement. You're always, with all of these modeling statements, you're telling Stan what the probability distribution is. And you can increment it directly if you have some way to write it down. Maybe that's not captured in Stan's modeling statements, but I think this syntax here makes it a little bit easier to understand what's going on. There's also an optional generated quantities block, which runs once per step. You can use this to perform simulations or make predictions. Okay, let's give this a try. So generate some random data, 10 different samples, and right now it's actually compiling that Stan model. It takes about 30 seconds or so. And what's going on under the hood is that we're passing that big string, we're passing it to the underlying Stan code. That's compiling it into C. And then the Pystan module is using Python to take that C code and compile it into a Python module that it loads into the Python namespace. And this actually can be pickled, so you can keep this compiled model around and use it in the same session, or you can pickle it, unpickle it later so that you don't have to incur this time penalty for compiling every time. And it will finish compiling any moment now. There we go. And the next step, this runs pretty fast, is the sampling. This is actually performing the MCMC. Feeding in the data, you give it this dictionary, and N, M, features, and Y. Let me scroll back up for a moment. That is the data that I defined in this data block, N, M, features, and Y. And then it's taking 1,000 steps. 500 of those are warm-up steps, which it's going to throw away later. Chains, it's doing this 4 different times. 4 different times it's going to start in a random location. It will take 100 steps through the probability distribution. Multiprocessing there. And you can look at the outcome. And this is what Stan gives you as the high-level summary output. We had 4 coefficients. Let me scroll up here enough that you can see it. So the coefficients that I used to generate the data were -1, 0.4, 0, and 0. And you can see that Stan has recovered that, -1, 0.4. And these two are a little positive, but you can see looking at the standard deviation here that they are consistent with being 0. Epsilon, it's estimating the uncertainty, the scatter around there. LP is the log probability. You can actually pull out the specific values that it's fit in the chains. That comes out as a dictionary here. And the beta portion, so 2,000 points by 4. 4 is the number of parameters you had. Beta is a vector with 4 different coefficients in it. 2,000, if you remember, there were 4 chains, 1,000 steps, but half of those steps were warm-up, which are discarded. So those are the 2,500 actual points from each of the 4 chains. You can plot this to see what it's doing. Usually you don't have to do this, but this is useful for diagnostics and if you actually want to see what's going on. So this is the first coefficient. The true value is -1. You can plot a histogram of that, and you can see that Stan is centering around the correct value of -1. There's a spread. There were only 10 examples going in, so it doesn't know exactly what that is. The data were consistent with anything broadly in this range. And Stan will also give you a summary plot. If you call plot on the fit object, you can see it gives you, these are the 4 coefficients, beta, the epsilon, and the chains for each of them. And if you don't specify an initialization, Stan will pick randomly for you, but you can pass in an initialization vector. I haven't done that here. You can also do a lot of tuning for MCMC parameters if you want to get into the real nuts and bolts, but the defaults are usually pretty smart. And this is model caching. As I said, you can pickle this. This is a long function which just hashes the model code going in, checks to see if you've already fit it, and retrieves it from a cache. I mostly copied this from the documentation. I'll use that in the rest of this notebook. So fancier, lasso regression. Something else you can do is add a penalty on your coefficients so that they aren't arbitrary sized. And if you're writing down the actual loss function, the function that you're optimizing, it looks like this. This is the ordinary least squares. You're adding an extra term. In lasso regression, you're adding an extra term equal to the sum of the absolute value of the coefficients. And this means that all else being equal, you want the coefficients to be as small as possible. Lasso regression is actually equivalent to putting a prior on these coefficients. When you're adding this to your loss function, you're actually saying, hey, I know that these coefficients are probably around 0, and they have a probability distribution drawn from a Laplace distribution. And this is what that model looks like in Stan, now without all the extraneous blocks. You can see here, I've specified a prior for these coefficients. Previously, I didn't tell Stan anything about what I knew about the coefficients, and so it was just drawing from an arbitrarily, a flat distribution. Here I've told Stan, no, it's not a flat distribution. I know something about how the betas are distributed, draw from a Laplace distribution. And I can fit that. and get out. Here I've really jacked up the lambda so that you can see the effect on the model. And now it's drawing these coefficients towards 0. You can see they're a little bit smaller than before. And I haven't done it here, but you can certainly also move lambda from the data block to the parameters block so that you are not just learning, you're not just inputting your lambda, you're having your model learn the best value of your prior from the data itself, which is kind of fun. Now, the 8 schools example is a basic classic example in multi-level modeling. And the outline of this is that it's from a 1981 paper. There's 8 different schools that were offering coaching on the SAT. And in each school, somebody went out and measured how much the SAT scores of the students changed after the class. You have Y, you have sigma, so these are the treatment effects and the uncertainties in each of the 8 different schools. Now, the nice thing about modeling in this way is that it makes you think about the problem. If you want to ask what is the actual treatment effect in each school, there's different ways to look at that. The first thing, the obvious thing you might say is, well, we measured the treatment effect in each school. It's right there. It's 28 with a standard deviation of 15. We got it, right? And of course, you don't need to write down a model for this, but if you did write down a model, this is what the model would look like. And running in Stan, you get out the inputs, treatment effect of 28, standard deviation of 15. But you might say, well, that's a pretty wide distribution there. Let me scroll back up. 15, 10, 16. That's actually consistent with all of them having exactly the same effect, which, they're offering pretty similar classes. Maybe they actually do have exactly the same treatment effect in each school. And if you make that assumption, the model looks a little more like this. There is, instead of a different theta for each school, you now have one theta, which is applied to all schools. And if you fit that data, you get out this. You get out a treatment effect of about 7.7 applied to all schools with some much smaller standard deviation. And again, you're putting into the model some information, something that you know about the way the world actually is. You either know that the schools are completely independent, there's no relationship between what's taught in one school and what's taught in the other school, or you're saying it's exactly the same thing is happening in each school. But you can certainly get more complicated than that. Partial pooling is, maybe some schools are doing, maybe they're all teaching basically the same program, but different schools are doing a better or worse job of it. Maybe they have different teachers, slightly different students, who knows? But there's some underlying treatment effect from the program itself, and then some modification for each school. And if you're writing that down in Stan, it's been the same data each time, same data in the data block, changing the parameters. So now you have, you're saying that the treatment effect in each school is on average the same, but there's some spread. So some schools will have a larger, some have a smaller treatment effect. Tau is me telling the model the possible spread in treatment effects from differences in teachers or whatnot between schools is equal to this. If you train that model, then it comes out looking like this. So you now have treatment effects on a school by school level and an average treatment effect. And here I've fed in a tau. I've said use tau of 25, but sorry, now I'm comparing to the original thing here. So you've shrunk your uncertainty a little bit, but still kind of large. Not bad though, we're learning new things about the data. But that tau, I selected the tau just kind of at random, and you can try different values of tau to see how the model changes with that. But you can also learn tau from the data. Now I've moved tau from the data block into the parameters block. And I guess I'll pause here. This notation lower equals 0. In data, what this is doing is it's serving as a check on the input. When you feed in the data, Stan is saying, oh, for the sigmas that you're telling me, they should all be no smaller than 0. If they are smaller than 0, it gives you an error. For the parameters, it's something a little bit different. For the parameters, it's actually implicitly specifying a prior. When you specify a parameter with lower equals 0, you can also put upper equals whatever. You're saying that this is not just a flat distribution from negative infinity to infinity. It's, well, in this case, it's a flat distribution from 0 to positive infinity. And it's important that you have good priors as you can when specifying the models. It helps the MCMCs converge to the correct value, and you also get better answers out if you include more information in the models. Anyway, in this case, I've moved tau from the data block to the parameters block, so now we're estimating that from the model. Again, theta is the school-by-school treatment effect. Theta is, one treatment effect for each school, and then you have mu, which is the average treatment effect, just how good the class is. And then you have, Tau, which is how much the actual implementation of the class can vary from school to school, maybe how easy it is to teach the course, how much the teachers are contributing. And you're telling Stan that your outcome, y, is normally distributed around this treatment effect, the school-by-school treatment effect, with some spread sigma, sigma being measured from the data. If you fit that, again, run the sampling, you get out this. So now it's picked a value of tau from the data of being about 7 plus or minus 6. And again, comparing this to the original inputs, you can see that we've changed some of these entries quite a bit. So the actual treatment effect of school 0 is not 12, it's not 28, it's actually closer to 12. And you can see these two values are consistent with each other, 12 with standard deviation of 8, 28 with a standard deviation of 15, but we've improved our understanding of what's going on in the schools by building in some knowledge about the data. And summary looks like this. So that's Stan, and Stan has a very large and extensive and well-detailed manual. If you go to the website, take a look, you'll actually learn a bit about statistics by reading through the manual. So it's a lot of fun. I encourage you to take a look. Thank you. We have a couple minutes for questions. It depends on the model, depends on the data, depends how many steps you're taking.
You can repeat the question.
Oh, sorry. The question was, is actually sampling from the distribution, is that faster or slower than the compilation step? Where is your time usually spent? In this case, most of the time was spent compiling the model. And for smaller cases like this, that'll probably be the case. I also regularly run into cases where most of the time is spent running the model. Compiling still matters, it's like half a minute or a minute, but if you're taking a lot of steps or doing some complicated model with a lot of data, it can take more time to go through it. Does that answer your question?
Another question. The parameter is what is where you specify the prior, right? So just to get an example, is that easy to change the prior distribution? So let's put it enormous prior or whatever.
Yeah, you can, well, in the parameters block, if you specify bounds like this, that's modifying the prior, but you would normally specify the prior in the model block, like this. And so for example, I could put here, like mu is normal around 0 with a spread of 1, for example. Or you could say it has a log normal distribution.
Okay.
Yeah. Other questions? Oh.
I saw it was about 20%. We open like correlated confidence counts, like
The question is, can you output correlated confidence bounds? Can you output the entire contour, basically? And I'm pretty sure the answer is yes. I don't know off the top of my head how to do that. But yeah, all of the information is there on some level. Yeah, you can, instead of inputting uncorrelated priors, you can input a correlation matrix and solve for that as well.
Thank you again, Stephen, for the presentation on that.